Hi class, this is a third video on electromagnetic waves and the relationship between the frequency and the wavelength of an electromagnetic wave. In the previous video, we worked through a problem in which we were given the frequency of an electromagnetic wave and we were asked to solve for the wavelength. And taking a quick look back at that problem, we were talking about these radio telescopes right here, which produce this image of a radio galaxy. And these radio telescopes were tuned to a frequency of 5 gigahertz. So they're looking at 5 gigahertz electromagnetic waves. So we solved for what the corresponding wavelength of those waves are by first converting that frequency into hertz from gigahertz. And then we took the speed of light divided by that frequency, and we got that those waves have a wavelength of 6 centimeters right here. So in this video, we're going to work through a problem in which we're given the wavelength and asked to solve for the frequency. And this will be a much more down-to-earth problem about the microwaves inside of your microwave oven. I'm sure you've all either used or at least know about these devices. So in your microwave oven, there's a device which creates microwaves, and it creates microwaves with a wavelength of 12.2 centimeters. 12.2 centimeters is about 5 inches in length. So that's the wavelength of the microwaves that are bouncing around and heating up your food. Let's figure out what that frequency is. So if we have the wavelength, we are going to first want to convert that wavelength into meters. So considering that 1 centimeter is 1/100th of a meter, we can move the decimal place 2 spots over to the left. And 12.2 centimeters is 0.122 meters. That's just converting from centimeters to meters right there. Now that we have the wavelength, we can plug it into our equation. So now we want to use the version where we have that the frequency of a wave equals the speed of light divided by the wavelength. And so we can just plug in the speed of light, 3 times 10 to the 8th meters per second, and then divide it by the wavelength, 0.122 meters. And so when you do a calculation like this, what we can do is just take 3 divided by 0.122, and that turns out to be 24.6. Your calculator will also have some numbers following this, but you'd want to round this to what's called 3 significant figures. You don't want to just write down all the digits that your calculator returns to you, because those other numbers are meaningless. You just want to keep the first 3 for this calculation. And so you take 3 divided by 0.122, you get 24.6, and then we still have times 10 to the 8th. And when you take speed in meters per second and you divide it by a wavelength in meters, the way that the units cancel out, what you're left with is 1 divided by seconds, and that's what a hertz is. A hertz is a 1 over a second, or it's a cycle per second. So here we have the frequency in hertz. However, if we want to use one of those prefixes that we discussed in the previous video, which is either kilohertz, megahertz, gigahertz, or terahertz, those are all at integers of 3 in this exponent. So for example, 10 to the 3 is kilohertz, 10 to the 6 is megahertz, and 10 to the 9 is gigahertz. So let's change that 8 to a 9, and that's what I did right here. So look at this step. I changed the 8 to a 9, but I want this number to still represent the same quantity as this number. So since I increased this side of the number by a factor of 10 from going to 8 to 9, I need to decrease this side of the number by a power of 10. So this goes up from 10 to the 8 to 10 to the 9. This goes down from 24.6 to 2.46. And the reason I did that is now I can take all of this, 10 to the 9 hertz, and I can replace this with gigahertz, because that's what a gigahertz is. Gigahertz is 10 to the 9 hertz. So anyways, your microwave oven, it produces electromagnetic waves which have a wavelength of 12.2 centimeters. That's equivalent to a frequency of right around 2.5 gigahertz. And so that's an example of going from wavelength to frequency. In your homework, you have a couple of questions which are pretty similar to what we've gone through in this video and the previous one. First of all, in question number 2 is very similar to the first problem that we worked through. So in question number 2, I'm giving you a frequency of 1,900 megahertz. So remember, a megahertz is 10 to the 6 hertz. So this is 1,900 times 10 to the 6 hertz. There's the frequency, and I ask you to calculate the wavelength. So you'd want to look at the previous video on electromagnetic waves, and we worked through a problem very similar to that. In problem number 1, this is actually very interesting astronomy question, or problem related to astronomy. There's a specific type of radio wave that is of particular interest in astronomy. We call it the 21 centimeter line, or the 21 centimeter wave. And this is the type of radio light that's actually emitted from neutral cold hydrogen gas. And there are regions in our galaxy and other galaxies where there is neutral cold hydrogen gas that we're interested in finding out where it is. And so we can find it by looking for this 21 centimeter line. So in this homework problem, I asked you to calculate what's the equivalent frequency of this 21 centimeter line. Oh, sorry. The 21 centimeter, that's the wavelength of the radio wave. So you have a lambda of 21 centimeters, 0.21 meters, and convert that into frequency. And this is just an example right here of what we're talking about when we talk about the 21 centimeter line. This is an image from NASA and also from the National Radio Astronomy Observatory, NRAO. So these images, they combine infrared images of this galaxy, M81. Those were taken with NASA's Spitzer Space Telescope. So that's all of this stuff besides the blue in these images. And then the blue is from the National Radio Astronomy Observatory, VLA. That's the giant array of telescopes that I showed you an image of at the beginning of the video. And these observe and look for that 21 centimeter wavelength light that comes from neutral hydrogen. So basically what they've done is they've taken those two images, one from a satellite and one from these radio telescopes. They've superimposed them on each other. And now you can see the galaxy at various wavelengths or various frequencies. And the infrared light is primarily from hot stars, and it warms up the gas and dust surrounding them, and it produces infrared light. And the blue stuff, this is from the 21 centimeter line. So this is indication of regions where you've got cold neutral hydrogen gas, and these are the regions where we expect new stars to form out of that cold hydrogen gas. So that's one of the reasons that it's of interest to astronomers to study this 21 centimeter wavelength electromagnetic radiation. There's other reasons as well. We will be studying this material about star formation and looking for clouds of cold gas in galaxies when we get to chapter 18. Chapter 18 is all on star formation, so we'll be coming back to this topic right here. So anyways, this wraps up the lessons on electromagnetic waves. We'll have some more videos on blackbody radiation and photons. Those are the other two really important topics in chapter 5. But to put this a little bit into perspective, all of these problems that we've been working through, they've all been kind of in this region right here of the electromagnetic spectrum. So most of these problems where we want to convert from wavelength to frequency are either for radio waves or microwaves. And what you'll find is, as we study blackbody radiation and photons, is that when we discuss the infrared and the visible and the ultraviolet, we hardly ever talk about them in terms of their frequency. We almost always exclusively use wavelength, or we're going to learn another way near the end of chapter 5 to distinguish these, not only frequency and wavelength, but we can also distinguish them based on their photon energy. So there's kind of 3 ways to describe and distinguish all these different types of electromagnetic waves.